How do we avoid premature optimization? Hello, my name is Eric Normand, and this is my podcast. Welcome. So I'm still talking about domain modeling. And one of the things that I do when I'm not at my best is I tend to approach a problem by jumping right into the code. And I believe other people do this too. I think it's very common. And when you jump right into the code, you necessarily or very likely are baking in a lot of assumptions that are really not safe to make yet. And a lot of those are premature optimization. So these, when we talk about premature optimizations, we're often referring to stuff like, you unrolled your loops too fast, or you thought that the bottleneck would be here, but it's really over there, so you really didn't need to optimize this piece of code. And those are all premature optimizations. But there's other optimizations that perhaps go unnoticed or go unanalyzed. So one thing that might be an optimization is, so like if you're developing an image library, you might begin by thinking, well, how do I best represent that image? It will be a two-dimensional array of colors, like bytes that represent colors. That also is a premature optimization. You have chosen a data structure very, very early. Presumably because that is faster, or maybe it's just because everyone else does it that way, and that's how you figured they must have thought it through and that was a good way to do it, or you just didn't even think enough about it. You just did what other people did. There's a bias there that we kind of lean on what others have done before. And that's the kind of premature optimization that I think that a good process of domain modeling can avoid. We just in general, people in general, but programmers specifically, we optimize too soon. We think of a concrete representation too soon. And once you've got that concrete optimization, lots of stuff becomes, or concrete representation, it becomes very hard. You don't know that yet until you start coding in it. Of course, it makes a lot of stuff very easy, like looking up the color of a particular pixel is easy. But what about looking up the color between two pixels, right? If you zoom in and you want to blow up your image, what pixel values do you put in there? Now it's not so easy, right? And then you have to make a copy that's twice on both dimensions. It's 4 times as big, right? You're making a copy of a big array. That's not so optimized anymore, right? So we need to slow down and have a step before we choose, at least one step, a whole phase before we choose the concrete representation. And that's what I want to present in my potential upcoming, maybe I'm going to write book. So what does that phase look like? It's basically uh, using algebraic thinking to explore what is really required in the domain. Then after you've done that, then you can start implementing. And what you develop out of the first phase, it could be a specification. And like I said in the last episode, you can encode that spec in a programming language or in English or some other language, even just pictures. You can encode it however you want, but I believe it's a good idea to encode it in a programming language. And so because it's in a programming language, you get a nice benefit, which is that you can run it. So you have kind of a runnable specification. And then the implementation is all about optimizing it, making it usable in all the ways that it needs to be usable. So what do I mean by that? Well, maybe you need to store the thing in the database and you just did it all in memory in your model. Okay, fine. Like, let's implement it so that instead of running over a data structure in memory, it's making a SQL query or whatever it is. That's all secondary. Primary is to get it working in memory. And this kind of has a lot to do with like live coding. Like, you know, we have these really powerful tools. We have a programming language, fast compiler, really fast computer with a ton of memory. We can run our specification like as a naive program, and it will probably work. It'll probably be good enough to run. You can play with it. You can see if it really does what you need it to do before you start deciding on concrete implementations, before you start making it work in all the in your stack, you know, with the database, and it's got to be async because it needs to run in the browser and all that stuff. So again, last time I talked about how I'm trying to identify these leading indicators that are even before clean code, right? What's typically called software design. Before that, into way before that, like identifying your operations and making sure that you've got a complete model of everything, trying to get rid of all the corner cases, all these like leading indicators, like number of corner cases, whether you have a good fit between your domain and your model, whether you've got all the operations possible. All these things are leading indicators that your code is going to eventually down the line be easier to maintain. The thing is, though, if you focus just on the maintenance, they're so far down the line, you're not going to be able to hit them directly. So we need to just put that aside. Maintenance, put it aside. Efficiency, put it aside. Even how could this possibly work? Put that aside. And in this first phase, you need to clear your mind of all that stuff, all those constraints, and really get down to the essence of your domain. What is it that we need to do? Those are your operations. What information do those operations need? And what are the invariants that the operations and the data need to follow? So the invariants are things that maybe relate to pieces of data, or they relate how two operations work together or need to work together. They might be simple, like this has to be a positive number, right? That's a simple constraint. But it could also be that this one needs to be 5 times that one. Or if we have this one, then we also need this one. Or it could be something like this function is the inverse of that function. Okay, these two operations are inverses. That's also an invariant that needs to be maintained. And so we need to step back from so I don't want to say from the code, but from implementation. And so there's like kind of a fine line that you have to walk where you're writing code because you're writing this runnable specification, but you have to be carefully not going down the implementation road and staying in a much more abstract place. And so those abstract things are things like the signatures. So if you think, what are the pieces of data I need to do this operation, and what will this result in, you get a function signature. And if you have a typed language, you can write that out as a type. You can write it out as a pseudocode type if you don't use a typed language. And so it's abstract because it doesn't have an implementation. It's just sort of like, I know that I'm going to combine these pieces of data into, and I call it data. That's even maybe too, that's a good thing to note. It's not about data, because you could be combining other operations with a higher order function, right? So you're combining two things in your model, or multiple things in your model into another thing, right? And if you got types, you can think about them as types. I like to think about them as types even if I'm not using a typed language, because I believe that types are very useful, whether or not your language gives them to you. We often think in types even if we don't have a type checker in our language. So you want to not think about like, oh, this has to be data. Like it might not yet. And so you're working at this abstract level where you're talking about types and their relationships and the invariance between them and how this operation converts or composes these things into a new thing, and all that's algebraic thinking. And working through all that, you can see corner cases like right away. It's magic. You can avoid them by saying, maybe this type doesn't really capture what I'm trying to say. Maybe I need something else. And you work through them, figure out, okay, I can do this. There's no corner cases. This is a total function, and I've got all of the ones I need. And look, also you start to see something like, I can implement these 5 in terms of these 3. So I really only need these 3 right now. I can deal with these later. You're starting to minimize the surface area of your domain model, and that's a good sign that you're finding some essence. Domain models, like the prototype that we're looking for, is something like Newtonian mechanics that has a minimum of concepts. I mean, really, it only has, 5 concepts, and then it has 3 laws that relate them. These are the invariants. So you have forces, right, which come in pairs, and then you have position, time, and then velocity is actually defined in terms of position and time. So it's dx over dt, right? So I guess you need derivative. That's a that's an operation that you need. So you can see how then acceleration is actually dv dt, and then forces, the sum of the forces is equal to the mass, so you need mass times acceleration. So you really only need mass, position, and time. And then the rest are kind of defined through invariance. And so that's the kind of thing you want to find, is some small set of operations and pieces of data and invariants that you need that totally define the system, right? Newtonian mechanics is a complete system. Doesn't describe everything in the world, right? It breaks down at the speed of light, or near the speed of light. It doesn't work. And it doesn't talk about size. It doesn't talk about, like, it's all point masses, but it is self-consistent, right? That's what you want. If you need to deal with size, that's a different domain. So there's this idea of scoping. What belongs in your domain? And you kind of have to explore, like, what if I bring in another concept? That doesn't really have invariance. It doesn't have relationships between the other pieces of data. Remove it. Well, what if I take this thing out? Oh, well, no, then the invariants just don't make sense anymore because they're all related through that. Okay, I have to keep it in. So your scope, you're constantly exploring that scope. You're exploring the surface area of it. And this is a thing that I'm going to have a lot of trouble talking about in the book. But there's a kind of, I want to call it magic. There's a kind of, something will click. There's insight in it. Like, it's insightful to leave that piece of the domain out. Because, wow, look, it gets much simpler, much more elegant. We can always add it in with another layer on top, right? With another model built on top of this one, or side by side with this one. And there's a click, and you have to sensitize yourself to that intuition, that insight of complexity and simplicity of how it's expressed, and the size of it and the scope of it. And there's a real magic to that. So a lot of I forgot to mention this, a lot of these ideas are inspired by Connell Elliott. He has a thing that he calls denotational design. Denotational design, like I said, I'm inspired by it. This is not denotational design. The reason it's not is because he's way better at math than I will ever try to be. I wish I could be like him. It seems really cool to be able to do what he does. He takes the algebraic thinking to the next level, and I'm hoping to take just a tiny bit from that, not go as far into the mathematical side, but tap more into an intuition about the scope and the size and the API service. Right, and so it was his idea to say it is premature to call an image grid of pixels. Really, you should the way I think of it is like, clear your mind, zen out, and really think, what is an image? What is it? Right, and that's something we can do because we are all kind of domain experts on images we see, and we've probably, at least as kids, colored and drew pictures, and we've seen a lot of images, seen TV, we've seen paintings, etc. So we're kind of all domain experts in that kind of what is an image. And his idea is it's a mapping from a location in a 2D space to a color. Okay, mapping from location in 2D space to color. Now notice he's scoped it. He's thrown out the idea of, say, a frame, like it is, like, say, rectangular, right? Or circular. You can have circular images. It doesn't have borders. It just maps location to color. And he doesn't talk about it in the talk, but I feel like he has explored and chosen to scope it down lower and say, we'll deal with putting it in a frame later. We'll deal with pixelating it later, which is basically sampling this function from location to color. We'll deal with that later. When we have to put it on a screen, we can do that. Okay, but he's really introspected into the idea, what is an image, and used his knowledge, his domain knowledge of that, and scoped it, really gotten it to the right size where he can say, well, now that it's just a function, I know a lot of things I can do with it. I can apply a bunch of algebra to it. Okay. And I can start defining operations. Oh yeah, look, I can define an overlay operation that puts one image in front of another. And I know how to represent that as another image, so another function from location to color, which basically is just saying, well, what happens if I take this color and I overlay them? And so there's some way of, like, say, mixing the color depending on like alpha channels and stuff like that, right? But he's deferring that to like the color domain. Okay, so he's really scoping this and playing with the scope, and he's found something where now defining the operations starts to feel really nice. Okay, this is the intuition, and the magic that I was talking about, kind of witchcraft that we're doing. We're really taking these ideas and boiling them down to their essence, and now what can we do with them? And he's writing it all out in code. It happens to be Haskell code, so he can write out types and things. But it just feels really nice once he's got it to the right spot. So I've talked about the magic, and the insight is, well, let's just punt on like an extent to this image. We can make the image infinite. Maybe there's nothing there. Maybe it's clear, right? The alpha channel is all transparent, right? Around here, on the outside. But we don't want to prematurely like say, oh, it has to be within a rectangle or some extent, even any extent. We'll let something else deal with that. So this idea of like stepping back, in his case, it's like freeing your mind to just, no, don't think about implementation. Don't think about optimization. Don't think about practicality, maintainability, all that stuff. Just think about the essence of it. That's the first phase. And write it down. Write it down in a language that is precise enough that it keeps you honest. Then make sure it's complete, that you've got all the operations you need, that you're sure that you can define this one in terms of that one, and you gotta make sure you can do everything you need to do. And he was sure, I can put it in a frame. He was sure of that. I mean, you can imagine how to do it. You can imagine how to pixelate it. Okay, I know how to do that. So then simplify. Play with the scope. Play with the representation, the type, right? Play with what is inside, how the operations relate to each other. Does it do what you want? Now, the cool thing is, this is what I don't think he does this. I mean, he doesn't shown it in his talks, but what I think is cool is that because you can write it in code, you can run it, even though it is way before you've implemented. You haven't chosen a representation yet, but it runs because you've written it precisely in a programming language. So that's amazing. So you can actually play with it and see if it, not just like intuit, is this enough? Will this work? But you can actually see it. You can do it and find maybe a faulty assumption just by writing an expression in this thing and running it and seeing, no, that's not really what I meant. Okay, so I talked about two things: this need to back up, think more abstractly about your domain, get precise, complete, and simple. Those are Connell Elliott's ideas. And I wasn't sure whether I'd use them, but they seem to be working. So this is way before implementation, way before choosing an optimization, using a lot of algebraic thinking. And then there's this other piece that you can use. You can build in insight. Last time I talked about how that there's something about a domain model that can give your business a business advantage, like a competitive advantage, not just like a cost advantage, like our software is cheaper to maintain than your software, but that we have an insight into the business domain that lets us do things better. Okay, so this could be, we have an insight into, if you're Starbucks, making coffee or selling coffee or whatever your domain is, we have an insight into it that lets us do it better. We have an insight into accounting and your needs as a customer, that a customer of accounting, that we can do it better. And it's that insight of scoping, figuring out what you're actually dealing with, and having this really elegant small API surface that cleanly, without corner cases or anything, can do the thing, right? So that's the two things. There's this working abstractly in a programming language, and then insight. Building an insight early. I do have time. I'm going to tell a little story that I heard on a podcast. I have a friend who has a podcast. It happens to be a Ruby podcast. Oh, now I got to look up. Right, the podcast is called Code with Jason. It's by Jason Sweat. And on a recent episode, he was talking about a domain, a business domain that they were dealing with. And it was all about documents and faxing and stuff. And so they had, in their model, they had a class called Fax. And he felt like something was not right with it. Like it just didn't seem to want to attract methods to it. And it just didn't seem to fit anywhere. And he realized, wait, there is no such thing as a fax. There's a document, and you can fax the document, but there's no such thing as a fax. It's not a thing. And it's something that we would say informally when we're talking. Hey, did you see that fax that came in, right? Or did you send that fax to that guy, right? Like we would say that. But that the insight that he brought to the model, to the domain model, was like, there is no such thing as a fax. We should just think about documents and maybe whether they're faxable, because you can't fax a magazine because it's got a spine, but you can fax, papers, a stack of papers, or a PDF or something, and whether that's faxable. Now you fax it as an action you take, and then a document comes out on the other side of the fax machine, on the other side of the world. But it's a document again. And it's that kind of insight that we need to capture, that we often use these informal ideas, and when we try to make them precise in a programming language, it's like, I don't get it. Why this doesn't work? This is so weird. Why doesn't it work? Okay, that's a good signal that maybe it doesn't mean anything. Scope it down. That's the kind of insight that I'm talking about. So thank you, Jason, for that example. Go listen to his podcast. Okay, I have exhausted this topic for now, and I'm out of time. So thank you so much for listening, and as always, rock on.